want to try to get through this last bit in chapter 24. There's still a little bit more to go in chapter 24 after this, but this is the last bit on radiation and re-radiation. So re-radiation we introduced last time, saying that we know that if we have accelerated charges that are going to produce radiation, those radiative electric fields will affect charges in other matter, causing them to accelerate, and they in turn will radiate themselves. Okay, so if we have, for example, a pulse coming in where E is pointing that way, and well, actually, let me draw E in the other color here, just to stick with something close to the book here. E pointing in that direction, and we'll say B is pointing outward, and we have, from the right-hand rule here, we know this pulse is traveling in that direction, positive x direction. And so it's incident on some matter. And so matter consists of atoms, okay? And so atoms have positively charged nuclei and electrons, electron clouds that surround the nucleus. So typically we're talking about electrons that are going to be the re-radiators, but not always. But let's say we just have an electron here. And so we have this electric field coming in, this radiative initial electric field coming in, call it E sub I, just to distinguish it from the re-radiation. And that charge is going to accelerate. We know that the force is Q times E. So this is a negative charge. It's going to accelerate downward. And if we have an accelerated charge, it's going to emit radiation itself. Okay? So this charge emits radiation in all directions except along the direction of acceleration. So just knowing that, we can start to think about why is anything visible, right? Why can we see objects that aren't directly emitting light themselves? And the answer is, okay, reflection. Okay, but what is at the heart of reflection? What is reflection? It is nothing more than re-radiation. Okay, this electron. So here, here's the light source. Here's a light bulb or something emitting light, and that light comes in, causes charges in some object to accelerate. Those accelerated charges are going to emit radiation in all directions, including back toward the original source, or down this way, or up that way, right? So if we're standing here, we would see re-radiation. Let's see. Remember, the direction is given by negative Q times A perpendicular. Okay? So we have an acceleration that way. Let's say our R vector is maybe back towards us, towards the original source. And A perpendicular is downward. And so we have negative times a negative times A perpendicular. And so eventually we'll see some re-radiation. Just label it re-radiation just to distinguish it here, propagating in that direction back towards us, okay, and in lots of other directions as well. But the light that we see reflected off of surfaces is nothing more than re-radiation from accelerated charges, the electrons in the matter, okay. And it's more complicated than that because we have lots and lots of electrons that are re-radiating in all directions, and then you have to add up all the electric fields, and so there's constructive and destructive superposition effects that lead to particular angle for reflection of a direct light source. But in general, it's re-radiation. Okay, so we can talk about reflection, we can talk about, we mentioned this at the end of class last time, we can start to think about why things are opaque. Okay, so we had a light source and we hold some object up to the light source and you can't see through this object. Okay, but we said that the superposition principle says that if I have sources of electric field due to two different charges, and they don't have to be accelerating, just any electric fields, the superposition principle says that if I'm looking at some observation location, I have to add up the electric fields due to all the charges in the universe. Okay? And here's charge 1. And so charge 1, I would have an electric field pointing in that direction, call it E1. And charge 2 would make an electric field at this location, also pointing in the same direction, maybe a larger field because it's closer, and that's E2. And then the net electric field would be just the vector sum of those. And the key idea is that the presence of the second charge doesn't somehow change the electric field due to charge number 1. It's still, in some sense, there. It's just that I've got to add it to the electric field due to charge number 2. So when you're doing superposition, you can essentially ignore each charge and find the electric field due to just that single charge and then add them all up later. Well, you're doing the same thing with radiation. Okay, you have this original electric field pointing upward, right? And now let's look, instead of back towards us, let's look at some location downstream. So here's R. Okay. And we have the original, sometime later, the original radiative electric field, again calling that E sub I, hasn't changed. Let's try this again. There we go. So there's a light bulb lighting up. And if I have some opaque object in front of it, you can't see the light, but in some sense, it's still reaching you. The electric field, the radiative electric field from the light bulb is still reaching you, but what else is reaching you? The light, I wouldn't say reflected, but re-radiated. The light re-radiated from the cardboard, right? And it works out that downstream, we have the original light, the original electric field, due to the source back here. We have A, accelerated charges downward, these negative charges downward. The direction, again, is given by negative Q times A perpendicular. A perpendicular is downward. We have a negative times a negative, giving us a re-radiation, a re-radiative electric field pointing downward. So if I have lots and lots of electrons, what will eventually happen? When I add all the radiation and re-radiation up, it's all going to, what's happening with the cardboard? It's all going down. It's canceling out, right? So I have just lots and lots of electrons, each contributing some re-radiation in the opposite direction of my original radiative electric field, and we're getting cancellation. And so the E net is smaller. And again, if I keep doing that, if I have another electron here that accelerates downward, I'm going to get some re-radiation again pointing downward, making E net smaller and smaller until eventually it would all cancel out. So if I have enough electrons, the contribution from all the re-radiation is canceling out the electric field from the original source. Okay, so we can understand reflection, or at least the basic idea. We can understand reflection. We can understand why things are opaque, just in terms of accelerated charges and radiation due to accelerated charges, and the superposition principle, which we've been dealing with the entire semester, right? So what? Well, let's try something here. Now, again, we're oversimplifying things because it is also the question of frequency, right? If I place my little detector here in front of the, what's going on here? Oh, it's not screwed in properly. That's why. That would help. I place my my detector here in front of our antenna. We've talked about this before. Accelerated charges going back and forth in the metal bar lead to radiative electric fields pointing that way or that way, which causes the bulb to light up. Well, if I place the cardboard in front, the bulb still lights up. Bulb still lights up. Now, so apparently there's also a frequency issue here, right? Because the cardboard will re-radiate a lot when we're talking about frequencies for the visible light range, but this is the radio frequency range, right? The wavelengths here are much larger than for visible light. For visible light, you're talking about a wavelength or wavelengths on the order of hundreds of nanometers. Whereas for radio, this thing is a decimeter radio transmitter. You're talking about a wavelength on the order of 0.1 meters. Okay, so it's 10 to the 9th times larger for radio than it is for the visible light. So apparently we can get these electrons to accelerate a lot or accelerate enough using high frequencies, small wavelengths like in visible light. But they're not accelerating that much when we're dealing with lower frequencies, larger wavelengths. And that kind of makes sense because what is this thing? Cardboard is a blank. If I can hold on to it. It's an insulator. So what do we know about insulators? What distinguishes an insulator from a conductor? No mobile charges. Okay, so the charges aren't that mobile. They're somewhat mobile. They can accelerate enough when we're applying visible light to the electrons in the cardboard, but they're not mobile enough to accelerate when we're applying a much larger wavelength, a much lower frequency. Well, what if we had a conductor instead? Okay, here's a conductor, sheet of just aluminum foil. This has mobile charges, right? This has mobile electrons. These mobile charges should be able to accelerate no matter what frequency we apply to them. And that's one reason why metals are shiny. You get nice reflection, nice re-radiation effects from the charges that are accelerating due to any wavelength we shine on them. So if I place this in front of place this between the antenna and the little detector here, what do you think is going to happen? Should go out, and it does. Because, well, what do I mean? What do we mean by blocking it? What do we mean by blocking it? That's right. The charges are accelerating in this metal foil, and they're re-radiating. They're free to accelerate as much as until they hit the edges, right? As much as they possibly can. And so you're getting sort of a maximum amount of re-radiation. And again, the re-radiation downstream is such that it's going to cancel out the original electric field. Okay, so if I have mobile charges that are free to re-radiate, I can reduce or even completely cancel out the original radiative electric field. Poke holes in this, like circular holes, or yeah, you might be able to have something like that. It would depend on. You might be able to, cancel out almost everything except for a tiny area, right? But again, there's an issue of the size of the aperture is going to, and how much you're going to see depending on the aperture size is going to depend also on the wavelength. Okay, so there's that sort of effect that's going on as well. But let's come back to another example where you do have something that isn't continuous. You have something like this. Okay. So we talked about last week or earlier this week. We talked about polarization polarized light or polarized radiation means that the radiative electric field is lined up only in one particular direction, right? So these charges are accelerating back and forth. So the radiative electric field is polarized along the x-axis for this particular object, right? That way or that way. So here's a question. We have lights or radio waves being emitted from this object. And I'm going to do the same thing as I did with the solid piece of foil. Thank you. I'm going to do the same thing as for the solid piece of foil. So here at location A, let me increase the size here. Here at location A is our radio transmitter. Here's our detector, light bulb detector. And I'm going to place the piece of foil with the strips in it, either the strips lined up in the direction of the detector or the strips perpendicular to the direction of the detector. In which situation is the light bulb going to light? What do you think? Okay, so half and half. And then some say both. Okay. All right, so let's think about what we just talked about. We said that here we have electric fields pointing either positive or negative x direction, alternating back and forth, coming out towards you, right? So it's polarized along the x direction. So that means I can detect radiation along that direction if my antenna is oriented that way. I placed the solid piece of foil here, and what do we see? Went out because the re-radiation coming from the foil is canceling out, right? We have accelerated charges back and forth, and so that is giving a re-radiation, again, oriented in the same direction, but just canceling out that original radiative electric field. So let's pose the question a different way. Which orientation is going to give us the maximum amount of cancellation or the maximum amount of re-radiation? Why A? It's oriented the same direction, so you'd think that we can get the charges to move along the long way and accelerate for a longer time, for example, than it was like this, right? Well, let's try it. It's lit up. It goes out. Can everybody see that? So it goes out, lit up. Now, it's not the perfect demo because my object here doesn't stretch the entire length of the transmitter, but you can kind of see it does make a difference, doesn't it? Okay. And, you know, this is one, people fall for the wrong answer for this one every time, so I'm not surprised by this, because it's easy to think about something waving this way, and you say, well, I got to put it that way to block it from moving back and forth somehow. But you really need to think about this idea of re-radiation. Which way are these charges going to accelerate? Well, if the original radiation is lined up in the x direction, you're going to get acceleration along the x direction. And I can get a lot of acceleration because the charges can easily travel along the foil strips lined up in that direction. But if I orient it this way, they're accelerating in the x direction again, but not for very long, right? Because it's narrow in that particular orientation. So we don't get as much re-radiation in this case as we do in this case, right? Make sense? Okay. Another application, what we just made is something called a Polaroid. Now, it's a radio frequency Polaroid. And you probably are more familiar with things like Polaroids and polarized sunglasses, things like that, right? So there's another, you know, there's a frequency effect going on again. But for visible light, what we can do is you have a piece of plastic, basically. And in order to make a visible light Polaroid, what you have instead of metal strips are kind of thin needle-like molecules, basically polymers, some sort of organic material that's kind of just a chain of molecules or chain of atoms in sort of a needle-like needle-like orientation or needle-like shape. And you get these sort of needle-like crystals, and they're originally all in kind of random directions. But if you apply a large static electric field, so I put these in the presence of a large static electric field. Well, we talked about induced dipoles, right? We know this is a review of early part of the course, right? We're going to create induced dipoles. We're going to get some amount of positive charge on one end, negative on the other, positive on this end, negative on the other, positive on this end, negative on the other, positive here, etc. And if these crystals are free to move about, then not only are we going to get polarization, but what would happen? Anybody know? What would happen? They would reorient, right? There's going to be a torque on these polar now dipoles, these dipole molecules, because I have a positive charge here, and so that's going to exert an electric force in that direction on the positive end, but a negative or a electric force in the opposite direction on the negative end, and these things will twist, right? And so you can get these things to all orient in the same direction. So we now have, and so we get this to happen, and then we cool our material down, and so we basically lock in these molecules all lined up in the same direction. Okay. So let's say we have visible light, and I'm going to draw this kind of in perspective here. So here's a light bulb. Here's a light bulb. And the light is coming out towards us in the positive Z direction. So that's positive Z. And now light coming from an ordinary incandescent light bulb is unpolarized. We could have charges in the filament accelerating in any direction possible. And so we could have light E-rad oriented that way, or that way, or that way, or that way. So along the plus or y direction, or plus or minus y direction, along the plus or minus x direction, or anywhere in between, any superposition of those two directions, right? So unpolarized light comes in looking kind of like that. Then I place my Polaroid in the way. So here is the Polaroid screen. And the molecules in the Polaroid, the crystals are lined up in that direction. What am I going to see out here when the light comes through? The sideways. What happens to up and down? It cancels out, right? We get re-radiation along the direction of these crystals. The charges for the visible light range, the charges can easily accelerate up and down the length of the molecules. They can't accelerate very well side to side. So we get re-radiation, which cancels out this original radiation in the plus or minus y direction. And so you end up with polarized light. Polarized along the plus minus x direction. Okay? And you can see, where do our Polaroids go? It just looks not as bright. I mean, you can still see through it, but it's just not as bright because 50% of the light is being lost, right? There's also some absorption going on, so there's more than that. But in principle, half the light is being lost from this polarization. What if I did this? What if I had another Polaroid out in front, but only now I have the molecules oriented in that direction? What's going to come through? Nothing, right? Because I've already canceled out the light that's polarized vertically. The only light left over is polarized horizontally. We've now got these needle-like molecules lined up in that same direction. The re-radiation will be along the plus or minus x direction. So I should be able to cancel everything out on the other side of the Polaroid. So let's try it. And let me see if I can do this. So here we have an overhead. I'm going to put one screen on top. So that is polarized in one particular direction. I put another Polaroid on top that's polarized in the same direction, but if I rotate it 90 degrees, that's not too dramatic. So let's kill the lights. Try it again. Make sure I got it lined up correctly. One on top, two on top, rotate it, and there we go. Got the light canceled out completely. Okay. So Polaroids are useful because, well, for sunglasses applications, you have the light from the sky. Light from the sky is actually polarized. Okay, and the reason for that is you have light coming in from the sun. Well, first of all, why is the sky blue? What's that? Reflection from space? Re-radiation. Okay, but yeah, re-radiation, right? Re-radiation. What is re-radiating? What is in the atmosphere? The molecules, in the air, right? Nitrogen, oxygen, and various other molecules in the air, which are being affected by the radiation from the sun, and they are re-radiating. Now, the blue color comes from something we mentioned a little bit early on, which is that when you're talking about acceleration, remember we said that the positions of these charges, these electrons essentially in the molecules, are oscillating sinusoidally. We're worried about the acceleration, right? So if we take the derivative of the position, we get a factor of omega, which is the angular frequency. If we take the derivative of the velocity, we get another factor of omega. So we have the amplitude times omega squared times sine of omega t. And no one can read that because this marker is dead. But I have a omega squared here, and omega is the angular frequency, which is proportional to the frequency of the radiation, right? So higher frequencies are bluer, right? Lower frequencies for the red end of the spectrum. So the acceleration, which is important for the re-radiation, right, because it's due to accelerated charges, we're going to get a larger acceleration for higher frequencies, and so we tend to see more concentration of blue than any other colors, right? The blue dominates. The sky's blue, and it also is polarized because if I'm standing here on the Earth, okay, and I'm looking straight upward in the sky, and here's the sun, and the sun's emitting radiation in all directions. So let's look at an air molecule up here. So here comes light from the sun, and again, that light is not originally polarized. It could be E-rad could be up or down. It could be in or out, so I'll draw that as a circle or an X that way. And this comes in, and here's an air molecule, and so the electrons in the air molecule could be accelerated upward or downward, or they could be accelerated inward or out of the board. But if I'm looking at the re-radiation from this air molecule, and now here's the source, and the R vector is pointing down towards me. If this air molecule accelerates downward or upward, am I going to detect that radiation? Or is there going to be any radiation? No, because there is no radiation along the direction of acceleration. Okay, so if it accelerates up or down, I don't see any re-radiation. But if it accelerates into or out of the board, I do. And that's polarized light because that light is polarized either into or out of the board. So I'm seeing polarized light from the sky, and if I have sunglasses that are set up to cancel out that particular direction of polarization, I can greatly reduce the amount of light entering my eye. Okay. So, and there's all sorts of other various applications for polarized light, but that's one of the most common ones. Okay. Questions? All right. What else do we want to talk about here? Talked about polarizers. We talked about why the sky's blue. Okay. Let's let's see, do we have any other questions here? Okay, we already talked about this, why the re-radiation, or why the light bulb doesn't light up. Let's try this one. This is a good one. This is just on simple idea of re-radiation. You have here a pulse of electromagnetic radiation, and the original radiated electric field is pointing downward. And the whole pulse is moving in the negative x direction. And there happens to be an electron at location A. So here's what's going to happen. This pulse is confined only between these dotted lines. This pulse comes in, and it's going to cause this charge to accelerate. But once this charge accelerates, it's going to emit radiation in all directions, including toward location B. So what we want to do is find the direction of E radiative at location B due to the re-radiation from the original, or from the electron. Okay, so it's a two-step process. You've got to figure out the acceleration of the electron, then you've got to figure out the direction of E rad due to that electron at location B. So let's try that out, see if you can do that. Okay, well, we've got a little bit of confusion here. We have one popular answer and answer number 2. This is there's a lot of steps here, a lot of steps you need to think about, because we need to think about the acceleration of the electron, and then we need to think about the direction of the radiative electric field due to that acceleration. So here's our original pulse, right? Pulse is confined to just this region. So notice that the original pulse is not going to be detected at location B. We're confining it just to that region. So there's B, and there's A over here, right? So here comes this E radiative, and it's propagating in that direction. So that's the direction of C. And so we have an electron here. So sometime later, E radiative reaches this electron, and it's going to accelerate in what direction? Straight down? Straight up, right? Straight up, because it's a negative charge. So we have a force upward, and that's the direction of acceleration. Okay? We now have a charge accelerating. It's going to radiate in all directions except along the line of acceleration. So we go through the usual steps of finding the direction of E radiative due to that accelerated charge. We draw an R vector that points from where to where? A to B. That's R. We draw an axis that is perpendicular to R, which is along that way, right? And so A perpendicular is which direction? Up and to the right, direction 2. Direction 2. So this is A perpendicular. Okay? And then the E radiative is going to be, when it reaches location B, E radiative will be same direction, because negative Q times A perpendicular, right? So a negative times a negative charge gives us an E radiative that sometime later, it's going to take some time to reach location B, but this E radiative electric field is going to be pointing in direction 2, which was the most popular answer, but not unanimous by any means. So if you had a hard time doing this, go over this, okay? Because it will be on the final exam, so you should make sure you know it.